Welcome you all to this video lecture. This is N. Manikandan, Assistant Professor, Department of Physics, Government College of Engineering, Bodinakino. The topics covered in this video are sound absorbing materials, sound insulation and its measurements, noise and its measurement, and impact of noise in multi-storeyed buildings. What is sound absorbing materials? The special materials used to increase the absorption of sound waves or to reduce the reflection of sound waves in a room or hall, known as sound absorbing materials. The requirements of a good acoustical materials or sound absorbing materials are as follows. It should have high coefficient of absorption. It should be efficient over a wide range of frequencies. It should be fire resistant. It should give pleasing appearance after fixing. It should have sufficient structural strength. It should be easily available at a reasonable cost. Classification of sound absorbing materials. The sound absorbing materials are broadly classified into four categories, that is porous absorbents, cavity resonators, resonant absorbing or panel absorbers, composite types of absorbents. Here the figure shows porous absorbents. When sound waves strike the porous material, a part of waves is reflected while the other enters the porous material. The part that enters the porous material is converted into heat energy, while the reflected part is reduced in energy. Fiber boards, soft plasters, rock wool, mineral wools, glass silk are the examples of porous absorbents. The second one is the cavity resonators. A cavity resonator is a chamber or container having a small opening. When sound waves enter the resonator, the waves are absorbed due to multiple reflections. The third one is the resonant absorbent or panel absorbers. Figure shows a panel absorbers. In this system, the absorbent materials is fixed on a framing with an airspace between the framing and the wall. It acts as a panel absorber. Gypsum boards, wood and hardboard panels, suspended plaster ceilings are some of the examples of panel absorbers. The fourth one is the composite types of absorber. Here the top and bottom layer are the panel absorbers and central layer is the porous absorbent. When the functions of all the three types described above is combined in a single unit, then it is known as composite absorber. The composite absorbers consist of a perforated panel fixed over an airspace containing porous absorbents. Now we are going to see about some of the common types of sound absorbing materials. Figure shows hair felt. The average value of coefficient of absorption of 25 mm thick hair felt is 0.6. The next one is acoustic pasta. This is also known as the fibrous plaster and it includes granulated insulation material mixed with cement. They can be fixed on the wall and their coefficient of absorption varies from 0.15 to 0.3. The next one is acoustical tiles. The absorption of sound is uniform from tile to tile and they can be fixed easily. Starboard is also used as an absorbing material. The next one is pulp boards. These are the soft boards which are prepared from the compressed pulp. They are cheap and can be fixed by ordinary paneling. The average value of coefficient of absorption is 0.17. The next one is compressor fiberboard. This material may be perforated or unperforated. The average coefficient of absorption for the perforated is 0.30. The next one is compressed wood particle board. This material is provided with perforations and it can be painted also. With a thickness of about 13 mm, the average coefficient of absorption is 0.4. The next one is perforated plywood. This material can be used by forming composite panels with mineral wool and cement asbestos or with mineral wool and hardboard. The next one is wood wool board. This material is generally used with a thickness of 25 mm. The average value of coefficient of absorption is 0.20. The last one is quilts and mats. These are prepared from mineral wool or glass wool and are fixed in the form of acoustic blankets. What is sound insulation? The art of preventing the transmission of noise inside or outside the hall or rooms of a building is known as sound insulation. The basic principle of sound insulation is to suppress the noise. The next one is sound transmission. What is sound transmission? The passage of sound into one room of a building from a source located in another room or outside the building is termed as sound transmission. Sound transmission occurs in four ways. That is direct sound transmission, flanking transmission, overhearing, leakage. In this figure, number 1 indicates direct sound transmission. Number 2 indicates flanking transmission. What is flanking transmission? The sound passes around over the top or under the primary partition, separating two spaces or rooms. The number 3 indicates overhearing, and the number 4 indicates leakage. Next one is sound insulation measurement. Sound insulation is normally measured by the sound reduction index, which describes the amount of noise reduced by a wall. The sound insulation is measured using 4 indices. The first one is sound reduction index. The second one is apparent sound reduction index. The third one is a normalized level difference. And the fourth one is standardized level difference. The sound reduction index is used in laboratory measurement, and in a field measurement, the apparent sound reduction index is normally used. Now we see about sound reduction index, R. It is defined as 10 times the common logarithm of the ratio of the sound power incident on a test specimen to the sound power transmitted through the specimen. That is, sound reduction index R equal to 10 log W1 divided by W2, where W1 is the sound power incident on a test specimen. W2 is the sound power transmitted through the specimen. The second one is apparent sound reduction R dash. It is defined as 10 times the common logarithm of ratio of sound power incident on a portion under test room to the total of the sound power transmitted into the receiving room and the sound power radiated by flanking elements or other significant components. That is, R dash equal to 10 log W1 divided by W2 plus W3, where W1 is the sound power incident on a portion under test room. W2 is the sound power transmitted into the receiving room, and W3 is the sound power radiated by flanking elements. The accurate sound reduction index R equal to L1 minus L2 plus 10 log S by A, where L1 minus L2 is the difference in average sound pressure level between the source and receiving room. S is the area of the free test portion in which the test element is installed in square meters, and capital A is the equivalent sound absorption area in the receiving room in square meters. Third one is the normalized level difference Dn. It is measured in decibels by considering the equivalent sound absorption area of the receiving room A and the reference absorption area in the receiving room A0. That is Dn equal to D minus 10 log A by A0. Fourth one is standardized level difference. It corrects the measured normalized level difference to the standardized level difference by providing the data in the term of the reverberation time T in the received room with respect to the reference reverberation time T naught, that is TNT equal to D plus 10 log T by T naught. The next topic is methods of sound insulation. The method of sound insulation will depend on the type of noise to be treated and the degree of sound insulation required. The methods of sound insulation can thus be classified into three main categories. The first one is sound insulation when noise is airborne. The second one is sound insulation when noise is structure-borne. The third one is sound insulation when the source of noise is in the room itself. First we see about sound insulation when noise is airborne. Sound insulation for the reduction of airborne noise can be achieved by the following methods. That is by avoiding opening of pipes and ventilators, by allotting proper places for doors and windows, using double doors and windows with separate frames and having insulating material in them, using heavy glass in doors, windows and ventilators. The second one is sound insulation when noise is structure-borne. Sound insulation for the reduction of structure-borne noise is done by the following ways. Treatment of floors and ceilings with suitable sound absorbing material and anti-vibration mounts, using double walls with air space between them, insulation of machinery. Third one is sound insulation when the source of noise is in the room itself. Following are the methods of sound insulation which are commonly used when the source of noise is situated in the room to be treated for sound insulation. That is, the walls, floors and ceilings should be provided with sound absorbing materials. The machinery like typewriters etc. should be placed on absorbent pads. The engine should be fitted on the floor with a layer of wood or felt between them. The sound absorbing materials should be mounted on the surfaces near the source of noise. Noise and its measurement. What is noise? Unwanted sound which does not give any pleasing effect to our ears is called noise. It is random sound. It does not provide information. It is a byproduct of industrial process and other activities. Noise is present in our workplaces and residential areas. Effect produced due to noise. It produces a mental fatigue and irritation. It sometimes affects the nervous system and lowers the restorative quality of sleep. Some strong noises lead to damage the eardrum and make the worker hearing impaired. The noises which are produced regularly will even retard the normal growth of infants and young children. One is noise measurements. Any sound in the form of music or noise can be measured in decibels. We may use phone and so also. However, noise can be measured in terms of two parameters. That is measuring amplitude in decibels, measuring frequency in hertz. Noise measuring equipments. Noise can be measured using the following equipments: sound level meter, sound dosimeter, octave band meter. So, measuring technique. Detailed analysis has to be made on the environment using sound level meters at several locations. Inside a building, measure the noise generated due to airborne, structure-borne, etc. using octave band meters. From the observations, we can calculate sound power levels for each and every area in most common measuring scales. That is sound pressure level. LP is equal to 10 log raised to the 10 P squared divided by P reference squared, where P is the sound pressure fluctuation above or below atmospheric pressure, and P reference is the 20 micropascals, that is 2 into 10 power minus 5 pascals, which is approximately the threshold of hearing. The last topic is impact of noise in multi-story buildings. Multi-story buildings is defined as the structure whose usage levels are regular in distribution and which correspond roughly to the required for human habitation. There are four main actions which causes impact of noise in multi-story buildings. The first one is speech privacy. The second one is background noise, example fan, AC, generator, printer. Third one is sound masking. The fourth one is orientation of buildings. First we see about speech privacy. It is an issue within office building, including individual workspace, inside conference halls and between offices. It mainly affects the quality of work in the adjacent office. The second one is background noise. It can adversely impact the workspace. Too little background noise and speech privacy is reduced, letting you to hear what is going on not only on workspace but also away from that. Third one is sound masking. It can be blend the building system's noise levels and exterior noise levels within electronic noise systems in the middle. Traditional sound masking systems are located in loudspeakers above the ceiling. The fourth one is orientation of building. A noise pattern can be more annoying in perpendicular rooms, and windows and perpendicular walls don't reduce noise as effectively as those on parallel walls become at the angle of sound. Apartment dwellers are often annoyed by noise in their homes, especially when the building is not well designed and constructed. In this case, internal building noise from plumbing, boilers, generators, air conditioners and fans can be audible and annoying. Improperly insulated walls and ceilings can reveal the sound of amplified music, voices and noisy activities from neighboring units. External noise from emergency vehicles, traffic, refuse collection and other city noises can be a problem for urban residents, especially when windows are open or insufficiently glassed. Okay, thank you.